Okay, well, it's going to be tough. So, Philip asked me to talk about multi-layer neural networks, and which are no longer old-fashioned. A couple of years ago, you couldn't speak about them. But it turns out that this is what I started with, so there was an interesting challenge, and things changed a little bit. So they become interesting because a number of success stories, like they achieve record performance, a number of benchmarks, and there are a lot of real applications, and some of them quite old that actually use this kind of technology. And I try to divide the work in three parts. First, speak about neural information processing, like NIPS, because this is what it used to be. Speak about the origins. Then an example, and the example I chose is quite amusing. I discovered it recently. It's Rumellart's propositional network, which is one of the early ones that was recently rediscussed by McCulloch in Nature, in the paper in Nature. Then I'm going to speak about the network construction kit and convolutional networks, and that should be okay for now. Tomorrow there is one about training multilayer networks and what's happening in optimization and why it's tricky and what kind of tricks we can use. And the last one is to look at complex tasks. And I guess it's going to be evident why I'm going to do this after a little time. So the first thing I'm going to ask you is about the perceptron. You know what the perceptron is, correct? So what is it? According to you. No, just say something. A single neuron model, yes? Good. That's it? I was hoping that somebody would tell me an algorithm, because this is what you hear most of the time. And in fact, if you look at the perceptron, this is a classical drawing of the perceptron, where you have a kind of retina. There is an associative area, which is plenty of things that are never very well described. Then you have the single neuron with the linear threshold units, and there is supervised learning of the weights using the perceptron algorithm, which is basically every time you make a mistake, you add your example to the weights with a polarity that depends on that of the mistake. But in fact, you have to see that the perceptron is a machine. So this is the associative area, or you cannot see really. So you see this guy, and he has a lot of wires. It's pretty much random wiring. And these are the weights. So this is Rosenblatt, and he has in his hand a set of 8 weights. Each weight is a potentiometer and little electrical engine. And whether it learns, it's bzz, 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 and the thing does the right thing. And I think that's important because at that time, this machine was doing things that the computers of the time couldn't do. Like you see the retina, and Bernard told me he showed that picture of the retina. And this is, I don't think this is Rosenblatt. And the computers of the 50s, they were completely unable to recognize anything of that scale. So the perceptron is a kind of an alternative computer architecture, an analog computer like they used to have at that time. And that raises the question, why is this that they had so many different kinds of computers? Like they could consider the perceptron as a computer, but also the latest IBM machine with tubes and ferrite. And for understanding this, you need to go a little bit earlier. And to something I believe is very important is this work of Wiener in 48, Cybernetics, which is the name of this institute, by the way. And in the 40s, they already had mature communication technologies. They could do radio, they could do phone, and Shannon had discussed information theory. And that was okay. Computing technology was completely at the beginning. And what Wiener did in that work was stating very clearly, for the first time with that clarity, that information processing was something generic, that it could happen in automatic systems, it could happen in mathematics, it could happen in the way we learn, it could happen in biological systems, it happens in society, and he proposed to study the information processing as a discipline per itself, to find the common principle that describe information processing in all these instances. That was not really computer science. That was not a computer. It was just studying information and how it's being processed and how it works. And Before that, when people thought about humans, they were thermodynamic engines, horsepower or power, watts, and motion, movement, heat exchange. And after that, we see humans as information processing machines. Everything you see in science fiction about the machines that become smart and everything comes back to this realization that there is some commonality that's deeper, and what's implemented in a human in terms of reasoning maybe could be implemented by a machine. It's not been proved yet, but that was the issue. So the question is how to design a computer. And you have two kinds of models. You have the biological computer. That's a model. Maybe we can design that. Or the mathematical computer, where you deal with symbols and you use the mathematical logic to derive the kind of computation you want to do. And the mathematical logic won. The computers today, they're based on mathematical logic. There is absolutely no doubt. A good question to ask why. So if you want to compute with symbols, you have a nice concept like a general computing machine, the Turing machine, the Feynman machine, and a lot of engineering. And the first part that's absolutely non-obvious is programming. Programming is reducing a complex task to a sequence of simple tasks. This is not obvious at all, and this is super important. And then computer language, debugging, operating system, libraries, everything we learn about computer science is based on that decision to compute with symbols. But if you look at something like the brain, take an engineering perspective on the brain. It's quite compact. It's energy efficient, about 20 watts, which is not bad. You have something like 10 to the 12 glial cells that they do pooling, power, cooling, support, architecture of the thing. They've put things in place. You have 100 billion neurons, which are a little soma and very long wires. You have a lot of connection, 10 to the 14. But if you think about it, 100 billion neurons, this has 128 gigabytes of SSD somewhere, so not that far. 10 to the 14 connections, it's true, we're far from that. Except that the connection in the brain takes 10 milliseconds to go. A connection here takes a couple nanoseconds. So we're not that far from the power of a brain. It's a new thing, but okay. And the volume of the brain is half the glial cells, and half the rest is wires, and the sum of the neurons is nothing in comparison. So it's just a lot of wires in a very little box. Now, is it a general computing machine? You could look at it in different ways. The first thing is that, yes, we can think logically and do general computing. We can emulate a Turing machine by following it, but it's going to be very slow. There are things we do very fast, like vision, language, social interactions. We do it instantly. So it's a very unbalanced machine. There are things that this machine is doing very well, and things that this machine is doing very poorly, although it's quite general, like mathematics, solving equations, or kind of reasoning. And in terms of evolutions, the most probably plausible theory is that it all started with vision, that animals started to have vision, look around, and that language is a product of vision, because the techniques you develop to analyze the scene, understand the object and their relation, find their way in language so that you can communicate them, and that logic is a byproduct of language. So that explains why logic would be so slow, because it's a byproduct of many other paths. So in 1943, McCulloch and Pitts invent a simplified model of a neuron, and they posit that this is enough to understand what's going on in the brain. So this is my fake neuron. These are other neurons. They have some activation, x1, x2, x3, xi. I multiply them by weights that represent the size of the synapses, and there's a matter of sign as well. And then you apply a threshold that gives you a 1 and a 0, and you go again. Simplified. And this is what you find in the perceptron. That's the single neuron that the perceptron uses. And of course, after that, people started to think about perceptrons, what they could do, because they could do things that computers of the time couldn't do. And so Minsky and Papert wrote this book, studying the perceptrons in some mathematical detail. And the book is a complex book, actually. It makes a number of points. One of the main points that you have to study things formally, but this is not the one that I'm going to be interested. The first one is that linear threshold units can be used to implement Boolean gates. And that's pretty trivial. Basically, if you take all your inputs, take a small weight, and have a high threshold, is going to do an AND. And if you use a low threshold, it's going to do an OR. The second point was that circuit theory is not very well known. Like, if you have a lot of Boolean gates, you can implement your Boolean gates in a wide and flat architecture. It's going to be faster, or deep and long. And if you want to know which families of function you can implement with something deep and narrow or wide, it's not very clear. And it's still unknown, actually. There are some ideas about the number of functions you can implement with a certain depth. It seems that when you allow more depth with the same hardware, you can implement more things. But this is very subtle and not very well known. The third point was that if you want to learn a deep circuit of Boolean gates, you have to solve the credit assignment problems. If there is a mistake somewhere, your set of gates do not do what you want, you can say that the last gate is doing something wrong because one of its inputs is wrong, but which one? And then you don't know very well how to correct back. Now, the strongest point was to define a number of elementary problems that need complex circuits. The first one is parity. So you have a number of inputs, and you want to know whether the number of ones is odd or even. And you can show that parity is actually very hard to implement with just gates like this. You need at least four depth circuit to implement generic parity. The second is connexity. Suppose you have an image, and you have a number of ones forming a shape, and you want to know if the shape is just one piece or not. And what they show is that if you have only local connections, because given the wiring constraint in the brains, you cannot have full connection everywhere, then there is no way to know whether the shape is convex or not. In fact, this is the problem of a maze. This little game that you have in books where there is a maze and you must see whether there is a path for the mouse to reach the cheese. And it's very difficult to do. In fact, when you see it, it's not absolutely obvious that there is a path. And the third problem is the problem of invariances. You have an image and you have an object at different places, and it should be about the same. So how do you do that with gates without having this invariance property inside? And the claim they make is that all these problems, parity, connexity, or invariances, they have simple algorithmic solutions. If you know what you want to do parity, connexity, invariance, you can write a program that's going to do it. So basically, they suggest abandon perceptrons and other analog computers that do learning, develop symbolic computers and symbolic AI techniques, because we can program these things, they're easy. Now, if you look in the light of what we know, circuit theory is still poorly known. Learning deep circuits means solving the credit assignment problems. It turned out to be easier than expected, but still a bit complex because it involves a lot of non-convexities. The fourth point that I forgot is that there are few linearly separable problems, that if you have not deep one-level network of Boolean gates, there are only few problems you can implement that way. But it turns out that this is the VCDIM argument. This is the argument saying that a linear system has low capacity. A linear classifier has low capacity. And low capacity is considered good if you want to generalize. So somehow the argument that says, listen, there are so many Boolean functions of n variables, and there are so few we can implement with a linear threshold unit, well, it's also the explanation of why linear threshold units can generalize. Elementary problems need complex circuits. Well, parity, connexity, or some invariances. Humans don't do that very well either. Parity, I give you a big image with a lot of dots, and I have to ask you whether the number of dots is odd or even. You're not going to do that quickly. You're going to have to count them. Connexity is the problem of the maze. If I show you a big maze and I ask you if the mouse can find the cheese, it's not obvious at all. You have to actually go and backtrack. Invariances, there is a typical example where you show to people faces upside down, and they would not even recognize their friends upside down. And the final thing, but have a simple algorithmic solutions, programming versus learning. Well, learning is necessary when the specs are not available. But there is something else here. How to reduce complex learning problems into simple ones? That's not obvious at all. And this is the reason why logic computer won, because you could reduce complex problems into simple ones. With learning algorithms, it's not there yet, and it would have to be done at some point. So anyway, let's go forward and look at one of these problems. And one of these problems is storing in a computer things about a taxonomy, living things, plants, animals, birds, fish, canaries, and fish salmon, and properties like is, can. So in the 68, Quillian came with this model where basically you organize the things into a taxonomy. Bird is an animal which is a living thing. And you store the generic properties at the highest possible level and the specific properties at the lowest level. Like for instance, bird has feather, but bird can move because bird is an animal, animal can move, and so on. Okay, pretty simple. This looks very simplistic, but this is what you would do in a computer even if you do it in a more complex way. And the reason for that is that if you have another kind of bird, or another bird, fish, and mammal, you would put mammal under animal, you would inherit the idea that animal can move and living things is living and can grow. And that's kind of nice. You know, all the discussion about object-oriented inheritance is about that, basically. Now, if you look at the psychological evidence, if this is true, then accessing specific properties should be faster than accessing generic properties. So people try to do that, did experiments, and they're actually quite hard to do properly and do control for everything. But once it was done and control for everything, the experiment is absolutely clear. Humans do not work that way. We're actually slightly faster accessing the generic properties than the specific ones. Can't work. So in the 80s, there was a group of people called the Parallel Distributed Processing Research Group, PDP, and they wrote a series of books. And a lot of people that maybe you know, like McClelland, Rumelart, Hinton. Hinton was there, it was in the beginning. And their claim was that neural representations are distributed, not to see single connection, single weight represent what you know. They're parallel. Then you reason in terms of processing units, connectivity, propagation rules, learning rules. And you have this famous sentence of Jeff Hinton, I want to know how the brain works, not necessarily at the micro level, but what are the principles that justify how processing units, connectivity, propagation rules, and learning rules are organized so that we can actually do something. So one of the examples was this Rumelart hierarchical attribute representation network. And so it's a feed-forward network. These are units exactly the same. They're not going to have to be threshold because of learning, but that's detail. You have items like pine, oak, rose, daisy, robin, canaries, and fish. You have relations, is, can, has, and you have possible answers. So in that case, you have the canary, you code a 1 here and 0 everywhere else. You code a 1 in can and 0 everywhere else. And you see can grow, can move, can fly, can sing. That's your desired output. And it's a very small network, but it's a non-trivial task because it's ternary. It's not simple correlation. Like if I change one bit here, I need a complete reconfiguration of my outputs. So it's not completely trivial. So the way you train it is that you replace the threshold unit by a sigmoid, which is almost the same thing. You collect training examples of item, relation, and the desired outputs. You form the mean squared error. You initialize with random ways, and you optimize by gradient descent. Time is it? Yes. So the propagation rule is that you have your xi here, you have the weights here that if this is the dot unit, I write the weight as wi dot. And the a dot activation is sum over all the units before of wi dot xi. And the state of your unit is your sigmoid times applied to the activation. Now, the back-propagation rule is for learning. It's just the chain rule. Yeah, I have a board. Suppose that what I'm going to call gi is the derivative of some error. going to be mean square error, over the activation of unit I. And suppose I know the GI on all these units here. I can use the chain rule and show that G dot is f prime of A dot times the sum over the post units of W dot J Gj. So how do I write this? Do I need to do the math? Yes, no, or it's obvious? An answer, please. Do it, okay. Aha. So let's go. The first thing I want to compute D of, so E over D of A dot. And I write it as D of E over D of X dot. This is how I write it. Times D of X dot over D of A dot. This happens to be f prime of A dot. And this, I'm going to decompose it even more, chain rule again, sum over all the things that come up afterwards. So over G belong to post of the dot. Of what? Of dE over dAj, dAj over d x dot. And this happened to be, I did write W dot J. Just a chain rule, nothing complex. And the same way, you can compute that dE over dW dot J equal x dot Gj. So when you have this, basically, you have the elements to compute all these derivatives. And the way it's going to work, the training algorithm, the batch version is repeat, clear a gradient accumulator. For each example k, set the inputs as implied by item k and relation k. Compute all ai of k and xi of k by propagation. For all output units, compute gik, which is f prime of the activation of this unit k times the difference between what it produces minus the desired output. And that's the derivative of the mean squared error. Compute all gik by backpropagation everywhere, and accumulate the gradient here. And at the end, in delta ij, I have the derivative of my mean square error over weight ij. I can just do a simple gradient update with some gain here that I'm going to adjust. So that's what we call backpropagation. You go propagation, backpropagation, forward, backward, and it's done. So it's quite quick. You have the stochastic version. For each example k, so instead of summing over all examples, you're going to take each example k, you do the forward operation, the backward operation, and you update immediately, instead of accumulating over all examples. Anyway, you train that way. What do you see? So here are some outputs of various conditions, like for instance, canary can grow. So I set input item canary, relation can, and I look at the grow output. And when you learn, you observe that, well, that's pretty clear. Canary can move. Maybe the interesting one is pine has leaves. So pine has leaves is going to go up and up and up and up, and at some point it's going to realize that no, a pine doesn't have leaf, even though it's a tree. And it's going to be down and go that way. Which is sort of amusing. It resembles what humans do. Now, if you look at the representations, so what's happening in this layer? So if you remember here that you have 1, 0, 0, 0, 0, 0, 0, what you have here in the activations is just a copy of the weights corresponding to the unit I. So when you're going to learn the weights in all this structure, you're going to learn a representation for each of the items. And what you see is that while you learn at the beginning, it's not very differentiated. just initialize with random weights, nothing's very clear. And you start learning, you start to see some differentiation between, let's say, animals, plants. And the more you go, the more you have differentiation at this level. If you do clustering in this space, so at the beginning, the clustering is about anything, like pine, rose, oak, and daisy. Oh, well, actually, you get quite quickly that animals and plants are different. And you go over, you start grouping the fishes and the birds and the trees and the flowers. And it goes on that way. Now, if you look at these representations, you do a PCA, you project them into a two-dimensional space, and you look, if you change the representation, what you're going to get in terms of the IZ relation. So you can see the space for canary, the space for robin, the space for birds, which is a bit bigger, the space for animal. So when you change this representation, you see the various things that are going to appear. And it's going to be amusing in other respects. Now, suppose that you add a new kind of animal, a dog. And suppose that the examples that involve dog are much more frequent. Well, at the beginning, everything's going to be a dog. You know, goat is a dog. Yes, goat is a dog, and then it's changed a little bit. And what's going to happen is that everything is going to be a dog, and then it's going to differentiate. So what you're going to see in the space for animals, that dog is almost everything, and then your system carves something for the goats and the pigs. And this was very interesting for the PDP people, because this is something that kids do. You know, at the beginning, kids, oh, this is a dog, and then you show a cat and dog, you show a cow and dog, and you have to say, no, cow, no, cat, and they slowly carve their thing. And you see the same kind of phenomenon there. So that was very interesting for the perspective. Now, you can do other things like change relations. So suppose you start training with just the is relation, or alternatively, the is relation is much more frequent. So what's going to happen is that at the beginning, the grouping in the representation space is going to be very bizarre, like sunfish, daisy, and canary. Why are they together? Because is yellow. So you start by giving, this is yellow, this is red, so you group everything that's yellow. When the other relation starts to come into play, your system reorganizes everything and eventually finds the correct clustering, the one that actually makes sense because of the ensemble of the relations. So that's a very early experiment. That was in the 89, 90, probably one of the very first. And that was very satisfying for the PDP people, because these things do a lot of things that are psychologically meaningful. Now, the thing is that we want to do engineering. We want to do big systems. We want to do machine learning with these kind of tools. And before going forward, I would like to show a construction kit that you can use to describe these systems. First, let's consider a linear brick. I'm not going to speak anymore about a threshold unit or a sigma unit. That's just something that takes x and w, computes the product y equal wx. And you can also backpropagate. If you know dE over dy, you can compute dE over dx by the chain rule, and dE over dw by the chain rule again. So this is a matrix. This is a column vector. This is a row vector. This is another row vector, and vice versa. But nothing complicated there. You can have a transfer function brick. So you have x and y is going to take x coordinate of x and apply a nonlinear function f to that thing. And the backpropagation rule, if you know dE over dy, so it's going to be a row vector here, you can compute a row vector at the input. And you can have a lot of transfer functions. So there is a complete list of things. There is the sigmoid, which goes to 0 to 1. There is the hyperbolic tangent, which goes to -1 plus 1, is a symmetric version of it. I used to prefer that one. There is a new one that Jeff Hinton introduced quite recently, which is max 0 of xs, which has absolutely no biological significance other than having interesting properties in terms of optimization, and we're going to discuss that tomorrow. Or you can do a ramp, which is basically something like this. And basically, I can enrich my catalog of bricks with bricks for all these things. I can have a square loss brick. So it takes an input and a desired value, and it's just going to compute the difference between my input and my desired value squared and half of it, which is the same as my square loss. And I can do backpropagation if I know dE over dy, which happens to be 1 because this is dE over dE. Then I can compute dE over dx and go on. And I have a lot of loss bricks. I can change them. Square loss, log loss, hinge loss, log softmax, max margin. Well, all these things, you can just make a list of pretty much all the losses you've seen in newspapers. And then I can have a sequential brick. My sequential brick contains a lot of other bricks. And the propagation is that I'm going to apply propagation rules to B1, B2, B3, and to the end. Backpropagation, apply backpropagation rule the other way around. So why is it useful to see it that way? Well, implementation-wise, it's flexible, it's modular. Lots of toolkits use this kind of things. It's convenient. What's important is the testing, because when you run this kind of systems, typically it doesn't work. And you adjust the parameters of the stochastic gradient, and it still doesn't work, or it works very poorly. It works sort of, but very poorly. And the thing you have to realize that if you compute the gradient wrong, it's still going to sort of work. So, but you can adjust the parameters the way you want. As long as the gradient is wrong, it's not going to work well. And it's extremely difficult, in fact, to debug that properly. You really need to control everything. So when you have these bricks, you can test each brick independently. You put it in a little harness that's going to do finite differences. And even if it's three lines of code, you're going to hit it with finite differences until you satisfy that it works. And in many cases, the 3 lines of code are wrong. And I must say, I wrote these 3 lines of code many times, and many times they were wrong for silly, completely silly reasons. The thing is that it's still going to work. If you just test it at the very end of the thing, it's going to sort of work, but not very well. So at least with this kind of implementation, you have a way to test every brick, and it's solid, you're confident. And you can invent other bricks that have nothing to do with biology, like a RBF brick, a vector quantization brick, and more. So let's give an example. So that's, you can see it in this website. That's the Google Street View dataset. So numbers in street views that are just segmented, and you want to recognize them. So they're little images. They're 32 by 32, and they're RGB. So basically, the number of inputs is 3 times 32, so 32. You have 10 outputs. You can have, let's say, 1,500 even units. So you make one of these sequential boxes. Oh, this is a reshaping box. You reshape the 32 by 32 by 3 image into something that's a size and inputs. The gradient is nothing. You have nothing to do. It's just wiring. You add a linear box that goes from n inputs to n hidden units. You add a tangent box, hyperbolic tangent box. Another linear, a log softmax, and the classification criterion. You want to train. So here is a silly way to do it. This time it's a mini batch, actually. For t, going from 1 to the training data size by step of batch sizes, you get the input and outputs as the next mini batch. And then you define a function that computes the gradient. Actually, it computes the value of the function and the gradient. So copy the parameter, set the gradients to 0, set your average function to 0. For all the inputs, call the propagation rule in your model, which is this sequential unit. Apply the criterion, accumulate the error, go backward, and yeah, that's it, backward, and accumulate, actually this thing accumulates automatically the gradients in the parameters, normalize by the number of inputs, and return the thing, and then you just do a GD step. Or you could do LBFGS, you could do change optimization. The important thing is that this function is going to call this function that you defined before. And that's the end of it. So, so this is a small example, and this shows that you can do small things that are psychologically interesting because they resemble things that we do. But can we do more ambitious things? And there is a very successful class of neural networks we are called the convolutional networks. So I'm going to try to speak about these first. The first thing that we know is that vision is fast. So that comes from Simon Thorpe. And you see something, you cross the retina in about 40 milliseconds, then you go to sample visual form in 60 milliseconds, and you go to high-level object recognition in 100 milliseconds. Now remember that crossing one neuron takes 10 milliseconds. All this was done by crossing about 10 neurons. There's no time to loop, no time for backtracking, no time for anything. It's completely feed-forward. And if you continue, well, there are going to be category of judgment, decision-making, motor commands to spinal cord, to finger muscle, 26 neurons. We go very fast. Given the speed of computation of our neurons, there is no way to have a way to go back and forward and everything. Just completely feed-forward. And this has been studied. All that's happening in this initial layer here and here has been studied and by, for instance, Hubel and Wiesel. And they just looked at the neurons. And their basic teaching is that there are two kinds of cells. Simple cells detect local features. Complex cells pull local features in some retinotopic neighborhood. So you take simple cells that fire in a certain area of your image, and you get some local features pulled together that represent a high-level thing, and then you do it again. So that was their evidence. And people thought about that, and they tried to do it in various architectures. So these are all things. Fukushima worked out on 74, the Neocognitron. So you get a kind of retina, and you get a little extractor that computes the things, and then you get this complex unit that do some pooling of things to try to get higher level, and then you pool again, and then you define a structure like this, all with more or less random weights, and then you apply a classifier. It sort of works. Can we do better? So here what we have. So we could have a full connection to the image, but that's too much wiring. You could have local connections where each unit sees only a part of the image with a set of different weights. And what you can do for invariance is you can do convolutions. So basically, it's local units, they do local connections, but the weights are shared, meaning that this unit is going to compute relative to this piece of the image, the same thing as this unit relative to this piece of the image, which is the same thing as this unit relative to this piece of the image, because the weights here are supposed to be the same. How to train with the same weights? Well, you compute the gradients as if they were different, and then you average the gradients. Now, you can do multiple convolutions. So now you have two kinds of units, the black one and the red ones, and they're going to compute two convolutions of the image. And of course, you could have multiple images there, and units that are going to take parts of two images and compute plenty of layers that way. All these images here are transformation of the initial one. So this was probably comes from a paper by 88 by Hinton and Lang, and was used quite a lot in the 1990s. For instance, in 89, we had nice isolated Hamilton character recognition system working. In 91, we worked on fast recognition or sonor image analysis. In 93, we were able to recognize vehicle in images. Like the application was quite nasty. It was recognizing ambulances versus tanks. So in 94, AT&T Bell Labs had a zip code recognition system that was able to work in the postal office. In 96, a check reading system reading the amounts of checks. I'm going to discuss that later tomorrow. And that was deployed industrially. It processed a lot of checks. That was real. And the kind of recognition systems that were used in these things, they would do convolutions. So you take your image, which is a character, So it's pretty much binary or gray level. You have convolution there 5 by 5, and you get 6 layers by doing this 5 by 5 mask. Apply the nonlinearity unit. Then subsample. So you get 14 by 14 now. So you go from 32 by 32 to 28 by 28 because there is the border issue. Then you subsample 14 by 14, and then you do it again with 16 and the convolutions 5 by 5 again. And then you apply the nonlinear unit, sigmoid, actually hyperbolic tangent in that case, subsample, and then you go to some fully connected network with hidden layer, hyperbolic tangent, linear layer, hyperbolic tangent, linear layer, hyperbolic tangent, 10 outputs, and you try to recognize characters. And this does non-trivial things, like for instance, this is a 4, and you see the various transformations of the 4 in the first layer, the normal one, the subsampled, then the next one, next one, next one, next one, next one, and this is a 4. But it can see that this is a 4, and this is a 4. That was not in the training set. Huh? Or this is a 3, and this is 8. And so that's pretty robust to this kind of changes. And I wanted to get my computer to work because I'll try to show you these things working. So I have code there somewhere that goes back from, probably wrote it in 1995. So it uses an esoteric Lisp interpreter that you don't want to know about. Okay, so I'm going to load some examples first. We had pretty sophisticated tools at the time because I must say at that time I had a little company in France and we were building software for these things because we thought that convolutional networks were really cool and they would be important. But nobody was really ready to believe us. So. We had an adventure. At some point, we had a discussion with the supermarket chain and they wanted to install a little camera on the cash register in order to know whether the person who is there is a man or a woman and have an age group so that they could correlate the person with what was actually in the cash, what they bought, to try to know how to resupply the supermarket. It was a nice project. So we built a little prototype. It worked quite well, I must say. And then we demonstrated the prototype. And then our customer started to be a bit afraid because it was time to go for the real project. And there was no longer change money. It was becoming a fair amount of money. So he went to see a specialist of vision in some university. And the specialist of vision said, there is no way to do this. It's completely out of the state of the art. So he came back, we said, it works. Yes, I know it works, but if something happens, and my boss is never going to forgive me because this big guy said it's beyond the state of the art. So the project went down. Well, now it's in the New York Times, but timing is important for these things. Anyway, so let's load the data. So this is a very small data set. This 480 example. I'm going to use 320 for training and the rest for testing or validation. I'm going to define a little network. So we had this nice tool to define networks. And because this used to run on a Sun 3 workstation, which is slightly less powerful than the first generation Palm Pilot. So this used to run slowly. And here, the problem I'm going to have is that it runs too fast. So I'm just adding a few layers to make it slower. So these are the various convolutions. So the input is 16 by 16. This is one of the convolution layer 8 by 8. And here I can see, I should click on it. Yes, that this is a Torres mask meant shared weights. In that case, connection. And I have my little dictionary of bricks here that I could use to connect things. And I go on that way. Anyway, I'm going to compile this network. Yes, so that's the description in the little Lisp language of that thing. Yes, I need to have my yes, I want that later, and I want no. wait a minute. Where is my? I want that one. It's just that I usually have a very large screen, and now my screen is reduced to the size of this thing. So, okay, so I'm going to initialize my weights. So there is a various smart way to initialize the weight that we're going to discuss tomorrow. Got some learning rate. I'm going to make it way slower because otherwise it's going to go too fast. I'm going to display some things so we can do some plotting. Okay, we're going to have this at some point. And I'm going to try to show the examples finally. Display. Let's do that. And I can go training set. Did you see? No. So I'm going to try to do it slower. It's amazing when you write something. When you write something 20 years ago, you remember it. I want that one. Yes. Okay. So what you see, the examples there. We didn't have a scanner, of course. They're mouse-drawn digits, so it's a recognizer of mouse-drawn characters. And the output is obviously plenty of crap, nothing interesting. So I'm going to stop this because now it's too slow. I'm going to get this up and up. And where's, yes, I want that one. And I'm going to start, I need to click this first. And of course I want this and this. And I want that one, but I want this one on top. And I want that one. Okay, let's go. So I keep the display because it slows it down a little bit. Otherwise, we wouldn't see anything. So the white is the training set performance and the classification, and the black is the testing set one. At some point, oh, it's working quite well here. I could divide the learning rate by 2 manually, so that, well, nothing special happens. Anyway, I'm going to stop it, because at this point, it's 99% on the testing set already. And I can try to show you this various set as soon as I can get the relevant window on top. Okay, so up, no, yes, yes. Okay, so this is the training set. So you see that it recognizes decently every digit. And I can show you the testing set because it's the real one we want. Huh? It also works. I can do little things like, do I have this? Add a little bit of noise. I could add more noise, it's still going to work. I can show you the various convolutions, I think, yes. So you see the various weights that are applied in the input layer. So you see here it's pretty much a horizontal detector. Well, that's kind of slide, maybe. Well,
can you understand how it works?
Well, usually in the first layer you can somehow, but at the second layer you see this one is taking these convolutions into that one, and that's not clear at all. So at this point, this thing is trained. It's a good recognizer for mouse-driven digits, mouse-drawn with digits. Sorry, and I think I'm going to stop here for the vintage 90 networks. Well, this is a much larger one. Nowadays, you train in a good half an hour. Yes. Yes, you must randomize them a little bit. It's a stochastic gradient descent, so you must randomize the examples or cycle to them in a way that alternate the classes. Also, it's a non-convex system. There is not a single solution. You have no idea that you reach an optimum there. You just kept improving the solution. So in recent years, there were some improvements. One of them is the pooling ID. So in what I showed in the little demo, there was just not even no subsampling. The convolution was applied with the window moving by 2 pixels every time, so I would have a lower resolution. And quickly we discovered that we want to actually shift it and do a proper subsampling. And then we realized that subsampling is not a very good idea because at sometimes when you see an edge, for instance, you're going to have an answer in the convolution that's going to be positive and then negative. When you average them, it goes away. So instead of doing the average pooling, which is equivalent to sampling, so this is the output of the convolution after applying nonlinearity. You could average them, which is subsampling, or you can take the maximum, which says that if you detect something in this little window, I want to propagate the detection up. Or you could do L2 pooling, where this time you take the square, you take the amplitude. And all this is actually things that people know about the visual system. It's just that we didn't read the papers. Or you could do LP pooling. And then there are other things you can do. You can do contrast normalization. It's something that we know that's happening in the visual system, that very often there is normalization. The simplest one is to apply a low pass filter to the image and subtract that. But you can do divisive normalization, works a little bit better. And if you look at the convolutional neural nets nowadays, it's becoming more complex, where you have a convolution and either hyperbolic tangent, L2 pooling, or one of these ReLU unit and max pooling, then contrast normalization, and then you do it again, and then you do it again, and then linear tangent category. So it's becoming quite deep. So, yeah. Is it more complex? Well, not really. You have a sequential model, you have spatial convolution, hyperbolic tangent, LP pooling with P equal to, spatial subtractive normalization. These are just bricks, they're ready to use. You just put them together and you train. Now, does it work? Well, Convnets in the 2000s were quite successful. Like OCR in natural image, on these 3D house numbers, this is a record. Traffic sign recognition, there was this GTRSB competition, they hold a record. Pedestrian detection on the area data sets, they did better than everybody else. Volumetric brain segmentation, that's a cool thing where they take slices of the brain, image them, and try to reproduce the various paths of everything. Well, anyway, MIT got nice results. Human action recognition. So there was something done in 2002 in NEC. That was the smart catch system. So that was the result of a kind of contract that people in California had with one of the airports. I think it was San Francisco airport. And there are plenty of doors where you must swipe your card to go through. And people would come in group, one swipes the card, and all the group goes. And they didn't want that. They wanted to detect that and sound an alarm when this happens, because everybody must swipe the card. So they install just a camera in front of the door, and then you see the people coming, and so you detect the people, where they are, and how they move. So you need to know the head, the shape, the shoulders, the arm. They swipe, they go, and you need to model the movement. And if you see several people going for one swipe, you start making a big alarm. So try to teach them not to do that. And I actually spun off a company that was called Vidient. I don't know what it's doing anyway. The Stanford did something on the Hollywood 2 dataset later on, or human action recognition works too. Object recognition, there was a NORB dataset that was not very well received by people in vision because it was very artificial. But there was a big splash with the ImageNet with Jeff Hinton recently, and I'm going to speak more about this. Things like scene parsing, which is labeling every pixel in an image to see which object it is, which is frankly not really scene parsing, it's just a kind of pixel labeling task. But there was some experiments in NEC and NYU. Medical image analysis, there is a cancer detection system that Hans-Peter Graf and colleague in NEC are doing, and supposed to be deployed as a second check in Japan. So these things work. Now, if you look at the ImageNet competition, it's an object recognition task, 1,000 categories, so it's no longer really a joke, 1.2 million examples, and these were the classical error rates. So the classification task is defined in the competition. It's having the right label among the 5 top labels recognized by the system. Basically, the state of the art was 25%, and Jeff Hinton and his 2 students, Ilya Sutskever is no longer a student anyway, got something like 15%, which was a big thing. You know, usually you gain a couple percent, you don't gain something like this. So that shocked a lot of people in the vision community, and detection was quite well too. So what's happening there is that this result become very serious and very famous because is one of those that shocked people in the group. The people in vision were shocked by this. I know a number of them, and they wanted to check it, make sure it works, and so on. And yes, it works. There's no doubt. So the network is convolu max pool norm cubed, linear relu linear relu linear. Now, of course, you have plenty of numbers and so on that define the exact structure. These numbers, shouldn't sweat the numbers too much. You know, they were dictated not by the experiments because they couldn't run that many experiments. They were dictated by what they could put on the GPUs. They used 2 GPUs in parallel. And Alex Krzyzewski, had this very good implementation running on 2 GPUs at the same time. And what they have is that they have 2 networks that are almost disconnected, except that once in a while there are a couple cross connections. And that's quite amusing the way they did that. They use this ReLU transfer function. There is something called the dropout trick. But you know, all these things, they change the performance by a couple percent. If you had tried one of the old convolutional nets on this ImageNet data with a fast enough implementation, they would not have been as good, but they would have beaten everybody else anyway. So these are small but significant improvements. And they also train on the full ImageNet, which is 15 million images and 15,000 classes. And they use this to help their training globally anyway. And you get things like this. For instance, they can see that this is a mite, and this is a container ship. Motor scooter, yes, look back, a leopard. That's interesting. This is labeled as cherry, because you have cherries. And the network is wrong. It says it's Dalmatian. Is that stupid? Anyway, what's interesting too is that if you look at the detectors that are in the first layers, you see they're cut in 2. You have the color ones and the black and white ones. And it seems that the 2 GPUs specialize on different things. And according to Alex and Ilya, this is quite robust. Every time you train, you see this separation. It's quite amusing. That one of the GPU, because the networks are separated, they just have a couple connections. One of them specializes on color, the other one specializes on black and white. It's quite good. Now, suppose you want to run something, because in the end, this is stupid. You take an image, which is 200 pixels by 200 pixels, you say what's inside. But in vision, you want a lot more things. You want to say where are things, you want to take big images and spot things in images. And so typically, you would do that by having a recognizer and scanning the image to find the things at various resolutions. And the wrong way to do is to take a convolutional network and apply them on various windows and scan it. Because remember, these are convolutions. They're invariant. So what you can do instead is enlarge your feature layers to a size that's compatible with that of the image and run the big convolutions and do it again. When you do this, you save a very large fraction. In fact, you get 1 order of magnitude more computation. You get 1 order of magnitude faster for this by doing this. So in fact, it's quite cheap to run convolutional networks on large images. And you can do things like recognizing faces in relatively large images. So of course, we don't really see the various recognitions. So this is a system that recognizes the face and the pose as well. So it tries to find and this is all the same network. And it can run in real time on a little piece of hardware that's optimized for it. Now, was this tried for speech recognition as well? Because you can do images. Can you do speech? No. Image is 2D. Speech is a signal, it's a sequence. And of course, it was done too. Like in '88, there were speaker-independent phoneme recognition. So it's the same thing, but instead of having two dimensions x and y, you just do a linear convolution with just one dimension, which is the time. So you have the pre-processing of the image that gives you a bank of filters, and you do well, same thing. So in '89, at the time I worked and could do speaker-independent word recognition. The difference was that they were using a big Alliance supercomputer, which must be as powerful as one of your smartphones. And I was using a very crappy workstation that was lower than the Palm Pilot, but I was using stochastic gradient. So instead of doing phonemes, I can do whole words. It was a big difference. And a couple years later, Xavier de Riancourt, who was in the same lab, we had continuous speech recognition system working this way. And you know, you can do things. You can take this, the codes that you get at this level and send them to a dynamic programming layer to decode and try to get the speech. Or you can do things like this, which is to have convolutional networks goes into a recurrent network where you have plenty of layers that go after the ones, and each one recognizes phonemes one after the other. And actually, this is something that they tend to do nowadays. What you should know is that in the 90s, the convolutional nets, or the time delay networks, they were competitive with the Gaussian hidden Markov models. But they were not that much better to justify displacing the Gaussian hidden Markov models. Some of them work well, but they were a bit tricky. You know, you have to get the gradients right and everything. So, no, people kept doing hidden Markov models because that was the way to go. In 2010, 11, 12, more data, more compute power, more results, and this kind of architecture start beating the hidden Markov model by a good margin. In 2011, 2012, basically all the major speech recognition systems switched to neural network acoustic models because they work better. And you see something that's quite generic. It's what happened with all this neural network deep learning story. What has changed is that things that were working already but were hungry for data and hungry for compute power, now are just working fine. Now, sorry, I went a bit too fast in my lecture. I don't know if it's going to be, I should keep for tomorrow, otherwise I'll be in trouble. I can try to answer questions. I can try to play with the little demo if you want. And, well. Yes, questions. Yes?
So you mentioned at the beginning that they're probably not that good in generalization. Is that still the case?
No, look at the little thing I ran, 380 examples, generalize perfectly well.
Yeah, but you have a lot of data.
In my demo here? Thousands of features and only a few samples. Of course, you're in trouble. This is why they never work really well on something like Caltech 101, which is very few examples. But I'm going to show you how you can actually go through that. This is something that people start to be able to do and involves using some transfer learning techniques. Now, if you want to do an image recognition problem and you have the resources to get a sufficiently large label set, do a Convnet, don't even think it's going to do it. The typical data sets that people used in vision at the time were, well, very often 2 images. Papers of that time in vision, there were 2 images, a pretty algorithm, nice, elegant, really, yeah, good, it looks good. Tested on 2 images. The Caltech 101 data set, there was a progress, they had more images, but not nearly enough to feed this kind of machines. Well, ImageNet is plenty, but you see the little demo I ran, which was this mouse-drawn characters, I just had 380 and that worked. And the network was already a couple thousand weights. So the generalization is reasonable compared to other machine learning systems. But if you want to go further and have, let's say, one-shot learning, learn to recognize a face in a single image, you have to use transfer learning techniques, and I'm going to discuss that later on.
Okay, here's a question. So at the beginning you said that there were different concepts of how to design the hardware as well, right? So there's the more logic-based hardware, then there were the analog computers. So do you think if now there would be analog computers or something, what could do the neural networks even better? Or
what's certain is that you can actually implement neural networks pretty efficiently on analog computers. Only the future will say. What I can tell is, I had something interesting to say, but I just forgot. You say about implementation. There were lots of analog computers in these times, because a lot of things were completely out of reach of digital computers. And it was also, like for instance, nowadays you might want to use an analog computer for very low power application. If you run these kind of things, like a convolutional network in an analog computer, you're going to have what? Something that can recognize faces in 1 watt, 2 watts, that's it? Or less?
What kind of analog computers are these?
Well,
how can I imagine, because I don't have much idea of analogous computer.
Okay. You want to do a sum of Wi xi. So you have your xi there, voltages. Xi is a voltage. Wi is a resistor. And then you have a current. They're going to sum the current here. You're going to sum the current here and use something like a little capacitor to accumulate it. And depending on the voltage on the capacitor, you go through kind of amplifier and you have a sigmoid and you go on. This is nothing. It's not very accurate, it's not very precise, but we don't care about precision, in fact, in these systems. In fact, things like the character recognition networks of AT&T, we try to run them by reducing the precision on the weights to something like 6 bits, works. You can reduce the precision of the calculation or even implement the sigmoid with, instead of doing something nice like this, you train it with that, but then you run it with this. On 4 bits of accuracy, it works, it recognizes. You have a little loss, but it's fine. So really it's a distributed representation. You know, you cut some weights in the network, it's still going to work. In fact, I don't know if I still have my network below. I mean, I can try to do nasty things like applying noise to the weights. No, I left it, sorry. Well, I'm not going to do that now. But you can apply noise to the weights and you see the performance degrade relatively nicely until a point where, of course, it falls apart. This was a regularization technique at some point to start cutting weights randomly and go on. Well, don't need to do that anymore. Other question?
So you mentioned that mathematical approaches won because programming allowed you to break down complex tasks into simpler ones.
Oh, yeah.
I see that neural networks, there is a toolbox that allows me to procedurally put things together, but have we actually broken down learning into simpler learning tasks?
Not yet. What we have is a modular way to describe models. Now, actually, if I go forward in my lecture, a lot forward. Yes. I want to show a slide that I hope is going to be at the very end. Yes. This is how I'm planning to finish my lecture. So how to design computers. So why do computers emulate mathematical logic? Because complex tasks are reduced to a combination of simple tasks. That's very important. It's called programming. And new ways to solve simple tasks immediately benefit everybody and everything. Now, if you look, sorry, it doesn't work that way. Remember the perceptron. It's an engineering necessity to do that. Now, simple learning tasks, what do we know? Classification, regression, clustering, multi-arm bandits, many other things that fit in an 8-page paper that you see in NIPS or ICML. They're simple tasks, all of them. Complex learning tasks, reading checks. Well, the check reading system was a big effort. It was a group of 12 people working for nearly 1 year to get something running, because it's full of complexities, it's full of images that are crappy, it's full of technical problems that were not solved at the time. No, it's large work. parsing visual scenes, finding objects and understanding their relations. You're going to do that with a classifier? No. Composing personalized web pages or placing advertisements. And then you have a problem of feedback. You know, you try a page, nice page with your advertisement and everything you want. But the problem is that you get only labels like clicks or returns on the page you show, not the other ones. So you start having an exploration problem. But at the same time, when you show a page, what's going to happen is that you're going to affect the behavior of the user in the future, and you're going to affect the behavior of the advertiser in the future because they're going to have different return of investment and everything. If you don't understand all these feedback loops, you're going to do crazy things. So that becomes a very large-scale causation problem. Natural language understanding. Well, that's a complex learning task, and it's hard to define what it is. We can define subtasks that are pretty well defined, but understanding, answering questions about a piece of text. You know, you read Romeo and Juliet, and you ask what's the relation between Romeo and Juliet, and maybe, well, anyway. And strong AI, let's dream. That's a complex learning problem. We don't even know how to start. So currently, I think the machine learning is in great danger because we have tons of little papers that do simple tasks, and when you have a complex task, or even mildly more complicated, like reading checks or composing personalized web page in a principled ways, it becomes hack, crook, and hook because we don't really know. We don't have a principled way to do this reduction of complex problems to simple problems. Now, if you do programming, well, we know sorting, we know filtering, we know well, a couple of others. And when you have a complex task like this, you can try to specify it, split it in pieces, and program all the pieces. And it's a task for an average mind, as my wife says. You know, you don't need somebody super specialized to do that. And well, it's compelling from an engineering point of view. And until we break that barrier, we're in trouble. And whether we do it with neural net or anything else, we have to break it.
How do you do unsupervised learning with neural networks?
It's just a loss function. So you just use the appropriate loss function. Well, I'm going to give you another example that I was planning to keep for tomorrow. So Ronan Colobert worked on this natural language tagging system, and as part of the transfer learning, he defined an unsupervised task, which is a language modeling task. And it basically generates positive and negative examples in the following way. Positive examples are segments of 11 consecutive words in Wikipedia. Negative examples are the same segment with the central word changed by some random word. And the loss is that you want the score of the negative example to be less than the score of the positive example. And then you get something that's quite interesting that's going to find internal representations that are going to be useful for other tasks. So that's an example. What? Well, okay. Yes, please. So what is right and what is wrong? The problem is, what is unsupervised learning? What do you really want? So take clustering, for instance. And clustering is just a manifestation of the prior you put in the way you encode your data. Because if you change the way you encode your data, you change the clusters. So for me, clustering is just something where I say, if I take 2 points, these points are close in my feature space, therefore they go into the same cluster, or these points are far in my feature space, therefore they don't go in the same cluster. So the feature space is not that obvious. Like, for instance, image, we take grids of pixels. You know, in the eye, it's not a square grid. You know, the density of pixels varies depending between the center and what's around. The color of pixels and the black and white are completely different in terms of their distribution. It's not obvious that the features are like this. If you cluster images in the space of features that's square grids in RGB linear response, you're not going to get the same thing as if you cluster images in the space of pixels that represent the variable density of receptors in the eye and the kind of log coding that they're going to do. So So for me, unsupervised, that's my point of view. People disagree, of course, but for me, unsupervised learning per se, I don't know what it means, really. I think it's just a way to not say the information we put in the system by other means, like the way we define the features. Yes?
So the convolutional layers, they share the weights, but the brain doesn't do that?
No.
And do you think there's something to gain to not share the weights?
Well, if you don't share weights, you increase the capacity quite a lot. One way to compensate for that is to shift the examples. So you take every example, but instead of showing them at the same point, you move them in your recognition field. And if you have the same distribution example in every position, the weights will tend to be the same. Invariants are not absolute, meaning that, for instance, if you have rotation invariance, which is quite hard to do with a convolutional net, by the way, full rotation is not correct, because if you take a 6 and you put it backwards, you get a 9. So no, it's not a full invariance, but a little bit is okay. So the answer to your question is, for humans, they certainly don't share weights, but we move our head quite a lot and we move our eyes quite a lot. So we get a lot of examples that are shifted.
You send the first somewhere, then we recognize it. You first send your vision on something, then we recognize it.
Well, you recognize in your peripheral vision as well. Huh? If your girlfriend comes on the side, you'll recognize her, I'm sure. I hope so.
I have a question about basically, in the very first example you gave with the taxonomy that has been learned. I've not done much neural networks. I've barely done them at all. But is it correct? I had the impression, I read that somewhere, you can also use it backwards and say, for example, set the bits for living thing, and then it's gonna go up on canary and robin and stuff?
It depends on the model. This is a very simple feed-forward one.
Okay.
Now there are other systems like Boltzmann machines that are bidirectional, and you can do all these things. They're more complex to compute.
Okay.
They prove less successful in practice because of that, even though now that you have the reduced Boltzmann machines, but they're still very slow. If you look at all the recent work on deep systems, they started with reduced Boltzmann machines and plenty of things, and they quickly moved to completely supervised feed-forward things because this is what works. But yes, in theory, this is possible. And if you wonder how the brain works, it's probably more complex than just feed-forward, but we don't know how.
You've shown one example with a quite complex structure of a network. How knowledgeable does one have to be to come up with such a structure? Is there any toolkit to
that thing here?
No, this one with the cube inside and plenty of layers.
Oh well,
in the end.
The convolutional network.
Yeah.
So this came out of looking the animals and trying to understand the thing. But these things like this, but the first thing you have to see that you're quite constrained, in fact. The mass size has to be reasonable enough so that you can see elementary features like kinks or lines in the image. So with the kind of image where the characters are a couple pixel wise, 5 by 5 is perfectly reasonable, and bigger is too much computation, so you don't do it. Now, how you subsample? Well, you subsample by 2 because why not? The kind of exact numbers, they're constrained by the convolution. If you have 5 by 5, this is 32 by 32. When you slide it, you're going to lose 4 points, so you're going to be 28 by 28. And you put 6 because, okay, you can try 4 or 6. But 4 is not enough. 6 is okay. 8 doesn't do much better than that anyway. Fine. You subsample by 2, get 14 by 14, and you shift your 5 by 5 mask again. Why 5 by 5? Because you have the code for 5 by 5. So
Okay, but why do you shift at all? I mean, if you already have an idea what the next layer looks like, then okay, they're parameters and they're maybe not that important. But what is the next layer? How do you know that?
What is the next layer? Well, you have this schema that becomes pretty convolve, nonlinearity, pool, normalize, and repeat. So pretty much know what they're going to be. And you have arithmetic constraints between the size of the layers anyway. You don't want to go down to just 1 pixel at the very end, so you're not going to stop after a little while. The deeper it is, the more difficult it is to train, so you don't do it too deep. And then you're fine. Huh? The thing is that you could try to decide whether you want to put 6 or 7 or 8. But you know what? You're going to lose your time. If you want the best performance, it's better to put more examples into what you have. Just make it large enough, put a lot of examples. It's faster than trying to optimize the sizes.
Before we go for the next question, could the people in the observation lounge say how many hands they see raised over there? Are there any questions?
No, actually, there are no questions.
Okay,
here.
well then we have enough questions left, so we can continue.
Hi, can you use multilayer networks for modeling state space models when you want to learn from a sequential temporal data?
Oh, how do I go to the space system to temporals only?
Whether you can model state space models with
I'm
multilayered.
sorry?
Whether you can model state space models with multilayered networks. For instance, if you have customers that you want to predict preferences over the time and you have sequential data.
Well, that I cannot tell you I know. So I can show you this one. That was a speech system where you had this recurrent network that was representing a state and that was trained on over a certain sequence of time. But if you have something with customers and regular interaction, it's going to be a lot more complex because the space between events can be very large. And so a system like this is not going really to work.
How do you relate those multilayer networks to hierarchical temporal memory?
I'm not sure I would use a convolutional network for that problem because I don't see how to do it very easily. Maybe it's possible. It's not the tool I would use. I would play causal games instead.
Okay, thank you.
I would play causation games, but that would be a very different talk.
Thank you. So I think related to his question and actually related to speech recognition, would one of the bricks here, for example, would you take an FFT at the front?
A what?
A fast Fourier transform. Would you actually take it to the frequency domain, or would you?
Well, the fast Fourier transform, typically in speech, the initial pre-processing is very fixed. You do a fast Fourier transform on Windows, and then you do a capsular transform, plus some there's some filtering before, and there is a kind of black art into reducing speech frame to a fixed number of features. Okay. And some people try to learn these things, but that becomes very difficult. Also, you see that if you again take the example of the ear, you see that a lot of this is done by hardware. Like we have the cochlea that does something like a filter bank. So it's close to be fixed. I said that's what people believed until they discovered that the cochlea is full of some liquids and there are little hair there. And people thought that the hair were just sensors, sensing the activation in liquids, but they discovered that the hair can move too, so you can actually excite the liquid in other ways. So nobody really understands what's going on there.
Okay, so but then there is that black magic before you actually give it to the neural network. So it's still a set of features that you're giving, which then is very similar to looking at pictures, for example?
In pictures, it's really pixels. We use really pixels, RGB.
Okay.
But the kind of pixels that the camera gives, which they're not photons. So there is always a certain level of preprocessing that goes with it. But in speech, there is a lot more.
Final question.
So are there machine learning tasks where neural networks do not apply?
Sure. Kernels. No, I mean, well, depends what you call machine learning. If machine learning is, machine learning, if machine learning is, 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 Okay, let's put it differently. I told you at the beginning that the brain is quite a specialized machine. So there are tasks that the brain does well. And neural networks, because of their initial inspiration, are sometimes well suited to this kind of tasks. Now, there are tasks that humans don't do well. Like, for instance, for a human, it's very difficult to sift through 1 billion web pages to find which one is the one you want and rank them. So, should we do this with a neural network? I'm not sure. It's not obvious. There are some use cases that are very good, like signal processing or image. They're really nailed by convolutional networks. I would trust a plane that would be piloted by a convolutional network using vision, or trust a car that's piloted that way. It's to that point. Now, if you take the kind of lexical access or hierarchical property representation at the beginning, but this one works well, but I know some that don't work so well, and we don't know why. At some point, people try to learn pretty much any function as a 3-layer neural network, and it's so-so, let's say it frankly. So yeah, your mileage can vary. I wouldn't say they work for everything, but there are some tasks that they do really well.